Good afternoon. My name is Mike Jamgochian. I'm with Alcatel-Lucent, and welcome you all to this session of NANOG 49, Understanding OTN and the Path to the Future. Really appreciate NANOG giving us the opportunity to speak on this subject this afternoon, and hopefully it will be informative for you, and really welcome any questions after my talk. So if anything comes up, please jot it down and come forward to the mic when I'm finished. What I'd like to do is spend just a few minutes giving a background on myself and where I fit with in the industry and Alcatel-Lucent. I've been doing telecommunications work for the last 25 years, and I've worked for MCI and Alcatel-Lucent, almost split half my time between the two. And in that time, I've done a lot with optical transmission and predecessor to that, electrical transmission and radio transmission. So this subject is pretty near and dear to what I do on a day-to-day basis. Currently, I'm part of the business development organization for the optics team within Alcatel-Lucent, but previously I've held a number of technical positions within that company and MCI. So my roots are in technology, and I've just moved into more of a business role. So this afternoon, not knowing how many of you are familiar with the transport end of our business, dealing in the alphabet soup that is acronyms on the transport side. Then a history lesson of where we've come from a transport perspective, kind of give you a background as to what led up to the Optical Transport Network standard. Go into an OTN 101, look at some network applications, the hierarchy of OTN, excuse me, and a concept that is new to this particular standard, and that is ODU Flex, and what that brings to the IP data environment that has not been previously available in the transport arena. And then look at OTN from a business perspective, what's really driving the need for this new standard, and where the industry as a whole is going. Many of you and your companies are really driving the need for these new standards and their higher bit rates that they bring with them in the transport network, whether they be with transport within inside a data center, or transport in a metro area, or transport long haul, or even globally. We're getting more and more global tie-in, so every piece of this puzzle comes together within the standard. Alphabet soup. Show of hands, how many are familiar with the transport side of the business? That's a fair number. As you guys may be aware, and sometimes I find even myself, having just casual conversations and talking in acronyms, and friends that don't know about the telecommunications industry are very puzzled by it. But there is a plethora of acronyms that are a part of the OTN, and for those who aren't familiar, ITUT is the standards body that has driven the OTN standard with participation of over 100 various vendors and service providers contributing to that work, not only here in the U.S. but globally. So this is for probably the first time so far, we'll see what happens, that this is truly a global standard. Every operator and vendor are driving to the same standard, unlike previous standards of SONET and SDH. Some key elements of OTN are the Optical Transport Network is the overarching standard that ITU has come up with, looking at trying to put more intelligence, and we'll go into some detail about that, into the optical layer of the network. And then OTH is the hierarchy that's underneath the OTN, and then ODU, OPU, OTU are various units, and I've got some slides that talk about how the hierarchy is built up. The optical channel, which is truly the information that is put over the light down the fiber, and that is built up into these three components, make up the optical channel. Forward error correction is pretty key in the optics arena, being able to send information along that allows you to correct for problems, impairments on the line, and improve the bit rate that is transmitted and the quality of that bit rate. We talk about low order and high order in the OTU standards, and we'll describe what those are in a little detail. And generic mapping protocol, and that is the way that IP, Ethernet data information is packaged up into a particular optical channel and transported across the network. Some other of these you're probably familiar with, but the key ones are over here on the left, and we'll speak more in detail of that. History, where this all began, and I only went back into the 70s because that was probably the culmination of and where the change really began. Up until that point, everything was in an asynchronous environment, running over copper, and then over time we began to see analog radio as the transmission medium. But this was dominated, as we all know, by AT&T. There was very little competition and very few advancements other than what AT&T was bringing to the environment. In the late 70s, early 80s, MCI came along and challenged AT&T and won in the courts and opened up the floodgates to a new business model within the transport arena, and brought in with it digital radio and fiber, and drove a change from the low bandwidth that was delivered at kilobaud and moved into megabit transport, and drove that in the 80s and 90s. And that allowed a number of other companies to come along and begin to provide services on ever increasing or ever decreasing cost of bandwidth. And then, as we all know, in the mid-90s, the internet explosion began, which many of you participate in today. And a lot of that wouldn't have been available to us if fiber and the associated SONET transmission hadn't been brought into the fore of the telecommunications industry. So in the late 90s, the drive was, as a transmission medium, pure fiber, making the interconnects over fiber, metro, and long haul and globally. So that is the dominant transmission medium that we have today. In the office, stronger and stronger coming along are Ethernet, carrier type quality Ethernet, but also because of the high bit rates, seeing some offices go to fiber to carry the 40 gig type rates today, and looking to 100 gig. Particularly if you're in a campus environment, fiber is used more and more as we move into the higher bit rates. So SONET transitioned. Ethernet became a critical standard to the business, as we're all aware, especially in the enterprise and in the data arena. And a lot of standards work was done in order to drive that into backbone networks as well. So with the advent of the split between TDM type services for voice, private line data that really wasn't IP based, and then the data play, the Ethernet, the IP video. As we've seen over the last 10 years, video is becoming a dominant, whether it's YouTube or the IPTV from AT&T or Fios from Verizon, and similar products from other service providers. Video is becoming a greater and greater drive of bandwidth within the network. What those two disparate technologies and standards really drove was the operators to ask, is there a way to be able to get all of these various types of services onto the same transport platform? Because as we see today, many of you may be involved in the difficulties of being able to drive bandwidth across a particular carrier's network and being able to get efficient costs and prices for that bandwidth, because the carrier's looking to try and consolidate. And if they can't consolidate into a single data stream from LA to New York, then the pricing for various services that we all try to acquire is more expensive than needs to. So the operators really were driving, is there a single standard, single type of platform that could be utilized to carry disparate types of services in their native form and be transparent to that, because there's a lot of intelligence that already exists in the native service, but it's very difficult to get the proper bandwidth consolidation across a larger network. So, some of the services work extremely well and are very inexpensive within a local area, but when you're trying to go from LA to New York with a particular service, it can get quite expensive because bandwidth is driving most of that cost. Plus the performance can be questionable at times, just because there isn't a lot of intelligence at the right levels within the network today. So the standards bodies took this up with a lot of input, and that's why today, in the last several years, we've seen the launch of OTN, and the likes of Alcatel-Lucent, Cisco, Juniper, Nokia, Siemens, beginning to deliver equipment that will support OTN, and the vendor or the operator community also taking up an interest in OTN. So the standard that is used for OTN was really started back in 2003, and it's an ITU-T standard G709, which really drove what OTN was to an operations environment, described what the functionality was, how the optical carrier was to work, and really was driven at the DWDM environment, because that's where the high bit rate at the time optics was, and that was the unintelligent part of the network. So trying to drive intelligence into that network to be able to deal with different types of services, whether they be data services or voice TDM type services. So what the standard does at its essence is developed an encapsulation methodology, and what they coined is a digital wrapper that would be put around the particular service that was trying to be transported across the DWDM network. And what that digital wrapper allowed for is to maintain the inherent service in and of itself, its protocols, all of the information that was necessary for equipment on the ends of the circuit to be able to process that, whether that was routers, switches, or voice switches, to be able to, or video equipment, to be able to drive that service across the network in a manner that has a structure to it, but does not impede what the underlying service intelligence is that is being transmitted. So this digital wrapper technique allowed for that encapsulation and then the aggregation on top of that to bring other services into the same optical channel. As with any standard, OTN specifies framing conventions and methods of doing performance monitoring so that the operators can get a sense of what is going on with their optical network at the DWDM layer and provide information that wasn't there previously. Prior to OTN being available, basically all you were looking at is transmit power and bit error rate. Those were the things that you cared about, and that was very little intelligence built in. Also, the forward error correction algorithms were very simple and straightforward and did not allow for a lot of coding gain. As the higher and higher bit rates became available, you needed more complex algorithms to be able to handle those. So a lot of the work back in 2003 was focused on 2.5 gig and the burgeoning 10 gig, but the standards bodies attempted to leave room for higher bit rates. And as we've seen today, a lot of 40 gig services are available, 40 gig interfaces on various equipment, and we're beginning to see 100 gig come available. Here this year, you will probably see a lot of announcements on true 100 gig type interfaces and next year services to go with them. So from a practical perspective, taking the basis of G709, then the standards bodies looked to how do you develop architectures in which you can utilize the OTN and digital wrapper, and that's where G872 came from. And in conjunction with 709 really lays out the total framework for this OTN network. It also gives an evolution, as we touched on here, beyond SONET and SDH. SONET was very, very good for TDM type services, but was not flexible enough for IP based services, and clearly struggles with video type services. So in the transport arena, really needed something that would drive not only higher bit services, but also video and IP based services. Also, this was driven towards a CapEx and OpEx view of the world, and being able to give the operators the ability to put, as we've said, various types of services onto the same wavelength, and being able to drive that. And if you can drive various services of different container sizes onto the same wavelength, then you can drive the cost per bit overall down. And if you're able to drive the cost per bit down, then you begin the spiral up of positive growth for the services that are out there. What the carriers were really looking for, and I believe has come about in the OTN, is the commonality that was required, as I've said, and being able to drive to a wavelength-based type of optical network, being able to put high data rates onto the wavelength, and being able to do that in a flexible way so that you can potentially come out of a router and go right into the DWDM, or depending upon the size of the network, as you get into much larger networks, being able to have a OTN switch be able to sit within the network, bridging the network between the IP data services and the TDM services onto a single backbone network. Transparency is the next key that the standard delivers. As I've said, the ability to maintain all of the underlying intelligence that an IP service has coming out of the router, and the optical layer not impinging on that particular information, and not corrupting or having to draw from that information, and the optical layer thus having its own intelligence and not reliant upon the router domain. Efficiency, just from the network monetization, what it's going to take to build these networks in the future, because you'll have a single standard in which the DWDM platforms are based on, and the ability to be able to take varying different types of services across the same wavelength, and maximizing the use of the wavelengths, and we'll talk about how ODU Flex does that on the maximizing the wavelength. And being able to support the evolution of data rates, being able to handle 40 gig, 100 gig, as we're seeing coming out this year and next, and having a framework in which 400 or terabit rates can be supported going forward, that are probably 3, 4, or 5 years out in the future. So let's look at the network and what, how OTN fits within the network, and what OTN is able to bring to the various aspects and various layers. As you see up at the top of this diagram, at the highest layer within the network, you still have the IP, MPLS routers and switches and the Sonnet SDH gear driving the services. Those can be voice services for cellular phones, landlines, all the way up to a video service such as IPTV or FiOS being driven across a network, and anything in between. All of that traffic needs to be able to be aggregated down into the layer 0 of the network across the wavelength. And previously, this was all done in segmentation, that the IP MPLS would be driven into this network, and the Sonnet SDH would be driven separately into this network. And there were either overlapping or inefficient wavelengths developed from that, because the two really never mixed. SONET extremely highly structured, needing to have all of this subdivision, and you had a way with virtual concatenation to try and stuff IP MPLS into that network, but it was very cumbersome and very difficult to do. So a lot of times these bandwidths were driven straight down, but then drove inefficiencies because it was very difficult to mix them with the SONET SDH bandwidths. So the OTN really subdivides into two pieces, a low order rate of being able to, depending upon what the bandwidth need is in the intelligence layer, driving a particular container here in the low order that is 2.5 gig, 1.25 gig, or smaller containers, and get them into an OTN container with the digital wrapper, no matter what their service is, and then be able to aggregate them up into higher order OTNs, 10 gig, 40 gig, 100 gig, and be able to put them on the DWDM network within the wavelength. So just as a graphic, being able to take IP, Ethernet, SONET video, and being able to put them into payloads and add forward error correction information and a header to provide information about this container now, and be able to pass that through a multiplexing arrangement and then out onto an optical channel. And you can have that multiplexing functionality here or not, and it really is dependent upon how large these containers need to be. If you're talking about a 100 gig container that is coming from a router and needs to get from LA to New York, more than likely there isn't much multiplexing that needs to be done. The router has already aggregated everything for you, gotten it up into the highest bit rate, and just needs to be put out on the optical channel. But if there is a lot of 1 gig or gig E traffic that is in these payloads, then it may be advantageous to aggregate those up into 100 gig transport rate and be able to pass them onto the optical channel. So a little bit further down, there in this optical overhead, there's frame alignment so that the equipment understands where this particular container fits with all of the other containers that are being passed. There's also overhead that is associated with this unit. And for the data unit, there is also overhead. So this is the full OTU that contains payload, the data unit, which is the payload plus its overhead, and then the FEC. So I'll have a couple of slides that really show this in more detail of how this is built up. This one in particular. So you're taking whatever the client signal is, you're putting that into a payload unit, and that payload unit has an overhead associated with it. That is then built into a data unit, and that has an overhead associated with it. And you bring in the forward error correction in that overhead as well. And then the transport unit is the combination of the data unit and the overhead for the data unit, and it has overhead, and then that is put into the wavelength, and then the wavelength is put out onto the line system. And depending upon the bit rate, it will dictate what information is stuffed into the overhead. So the rates that have been defined are here at the transport unit, and this is the actual information that is put into the wavelength and then put out onto the line. They also defined a data unit, and in order to support Gig E, an ODU 0 was defined so that you had enough room within the payload to be able to support down to a Gig E, and then the associated rates as we go from 1.25 gig all the way up to 100 gig. You'll probably see people interchange OTU and ODU when they talk. It's just a common habit. I think everybody likes to get to the least common denominator, so you'll see people reference one or the other, whatever they're comfortable with. But really the distinction is in the OTU, what is put out on the physical wavelength, and then ODU is what's the data unit that is underlying what's out on the physical wavelength. And then what the true signal rates are, and that includes the overhead for the OTU, and then what the payload rates are within each of the generic rates. So you'll also see a lot of people speak to the marketing rates, but know that underlying there are very specific rates to be used as a part of the hierarchy. This just gives you the framework. As you'll see with ODU Flex, you'll be able to cross between these payloads and be able to define a customizable size by aggregating various different payloads together. The G709 standard, as it stands today with Amendment 3, was ratified at the end of last year, and what Amendment 3 had brought in were the ODU 0 that previously wasn't there, the ODU 4, which is the 100 gig rate, which was not previously there. It also set up that to be able to move towards higher bit rates by defining a ODU 4 as either a high order or a low order. So it can be the one and only container that is in the wavelength, or it as a high order, or it can potentially in the future be a low order, which is then mapped into a higher order container. An ODU 2E rate was defined, and we'll speak to that here in a few slides. That was something specific coming out of Asia, driving for a particular flexibility in rate structure to handle some IP services. 40 gig, 100 gig base R for parallel 66B interfaces. Some transcoding was included for fiber channel, and that relates back to the OPU2E, and delay measurements were included as well. What I want to talk to first is the blue area, and unfortunately I converted this to send this in. I ended up using Adobe Acrobat, so and it's in PDF form, so I didn't attach the animation. But the blue really talks to where G709 and OTN started. The objective to begin with that I apologize for not stating this up front, was to be as simple as possible, to be very straightforward in the mapping arrangements that were defined, and not make a very complex hierarchy. Being that as it may, a lot of you may have been involved in standards work, find over time with a large number of participants in a standards body, things change, and not always for the simpler, but more likely for the complex. So what we've seen over time is the addition of the red items in the mapping, and going from something that is fairly straightforward to something that is more complex. And what this drives is equipment to be able to handle this complexity. Vendor community was really going for a simple architecture in order to drive overall cost down, but still being able to provide flexibility. However, varying operators were driving for their special need, their niche type products that they wanted to, and services that they wanted to provide. So you begin to get a more complex arrangement. So just simply, this is where we can clearly define a low order and a high order ODU, and the subsequent OTU that then is put out onto the wavelength. So you can have a ODU1 as either a high order or a low order. And really the difference is does that have any underlying low order? If you're a high order, you definitely have underlying low order services as part of your container, and you have had them muxed up into you. So an ODU can be muxed up into an ODU1, ODU2, ODU3, or ODU4, and the only difference is the number of ODU zeros that then are contained in each one of these, but they're all ODU 0 based. ODU1, if you are the low order, then you go straight into an OTU1, but you can also then be multiplexed up into an ODU3 or an ODU4, ODU2 through ODU4, and then put out onto the appropriate line system, and so on. So then also there is the ODU flex that comes in, and that is only able to be put into an ODU2, 3, or 4 because it's all based on ODU 1s. Or it's actually based on ODU zeros, excuse me, but they precluded the ODU1 from that because this was really driven at the 10 gig and above multiplexing. So I want to spend a little time going through each of the containers. The ODU 0 is the smallest container that is defined, but as I've said, it cannot be put on to a wavelength. An ODU 0 has to be then multiplexed up into a higher order ODU 1 through ODU 4 before it can be put out onto the wavelength. So anything that GigE and below that needs to be aggregated up will be put into an ODU 0 and then placed either into an ODU 1 or above. They've also defined the number that can be placed into the various ODUs from 1 through 4, and the types of services, the underlying services that the client can provide. and I've already stated that it is not a physical interface or physical container that goes out onto a wavelength. And ODU1 is the first point in which the OTN is then put onto a physical wavelength. We've talked about these rates, and it can either be subdivided into two 1.25 gig slots or be the full data rate. And it's really driven for these types of underlying clients. ODU2 is 10 gig, so we were going from 1 gig or gig-E to 2.5 to 10 gig. Same kind of arrangement. It can be subdivided or have the full bit rate. And then this is where you introduce the ODU Flex, so you can have 1 to 8 time slots defined within the ODU2 for building up specialized containers. And so if you have a 12 or an 8 gigabit service that you want to transport, you can use ODU Flex to encapsulate that and treat that as a contiguous piece of information, and then still have space for a couple of ODU zeros to be put into the same overall ODU2 container. So you have that flexibility of being able to build up these specialized containers with ODU Flex, and then also multiplexing back in to fill up the whole container so that you're not wasting bandwidth. ODU2E for the fiber channel, and this was coming out of Asia, as I said, specialized to be able to better handle the fiber channel. Same structure with the ODU3, driving towards these types of services, and you continue to get an increase as you go up the hierarchy of the capacities that are supported. And similar to ODU4 at 100 gig, and being able to drive in that data rate. So ODU Flex, this is something that was a recent addition. There's still some work to be done on ODU Flex. The basic framework has been ratified, so you can construct an ODU Flex container. The thing that is still being worked out is the ability to dynamically size this container as bandwidth needs change. That is one of the ultimate goals to make this totally flexible, is that as a particular flex container is set up, as traffic ebbs and flows across the container, being able to dynamically size that container to the bandwidth that is needed within a particular time frame. So that work is still ongoing. There's some challenges on how you dynamically resize this, because one of the key goals is not to impact the existing traffic that's running over the ODU Flex container. So being able to set up protocols to allow for this dynamic resizing still needs to be worked. But I think the key is now having the ability of a container in this space that can be sized appropriately for varying different underlying traffic needs. And as you can see, you can have ODU Flexes in a higher ODU container. So these ODU Flex containers can be of different sizes and then multiplexed up into a higher order container. So with the drive to more and more 100 gig services on the backbone, you'd be able to better utilize those 100 gig services with the drive of video or IP, particular data center needs that fluctuate depending upon the hour of the day. So those types of services that change over time can be implemented within these containers. And the containers can be segregated into either circuit-based containers or packet-based containers. This gives you the flexibility of making sure that those two networks are serviced as efficiently as possible. I've spoke to this, and just as a recap, there's still work to be done in the resizing arena. That is the ultimate goal of the standard is with ODU Flex is to be able to dynamically resize, but they're still working on that. So it may be a few years before that capability is available. So as we've talked a lot about this afternoon, is all these services are really putting pressure on this overall backbone, and the current backbones that are deployed with SONET SDH are just not capable of sustaining and supporting the growth that is coming at them from a service base that is so varied. Also, one of the things that you begin to have trouble with is when your growth begins to outstrip your ability to generate revenue. And we see that more and more as we move forward. Each of us as a consumer are not willing to pay very much for the services that are delivered to us. The free internet, though as democratic as it is and as open as it is, does create some problems for being able to be a sustainable model. Because what our customers are all looking for are higher and higher bit rate services at lower and lower costs. So if you continue on the path here and you've got a disparate traffic growth and the cost of your network continues to follow the traffic growth, then you've got a disconnect. And the model no longer becomes sustainable. So what we've seen too is this hierarchy, this inverted pyramid, where the IP routing has always been extremely intelligent, extremely robust, but it also bears a cost. There is a cost to that. And as you move down closer to the lowest level of the network, the cost per bit is extremely low. So really, not only cost, but we're seeing a drive in power consumption, floor space, everything is driving a very costly overall IP network. And really the objective is to figure out what the underlying traffic really is and where that traffic really needs to be processed. I mean, I've been working with a particular customer right now who's struggling with this. Their entire network of data traffic is being processed by their layer 3 switches. Every layer 3 switch touches every piece of traffic within this customer's network, and it's an extremely large network. And what we found was, when you really dig into it, about 40 to 60% of that traffic at any one given node is never processed by that layer 3 node. It has to pass through that node because you've got a fully connected mesh network, but it never processes it. So this customer is driving their IP vendor to build bigger and bigger routers to handle larger and larger traffic, but a majority of the traffic just has to pass through that physical site. It doesn't have to pass through the router. So one of the advantages that comes about with an OTN type architecture is the ability to look at something in the layer 2, 2.5 area to be able to deal with that traffic that at a particular site is not being processed by the layer 3, and take and utilize the layer 3 for what it does best, for that traffic that is entering that node and then having to get out onto the network. But if there's traffic that's just passing through, bypass the router. Get away from the router, process it somewhere else, and only let those routers deal with it that actually are processing that underlying traffic. So that's where OTN comes in, is being able to allow you to rethink this architecture and get some more efficiencies in, and also drive the overall cost down. Because if this IP layer is truly as costly, if it continues to be truly as costly as we've seen today, and the switches and routers continue to get larger and larger for processing less traffic, you can actually remove traffic that is not requiring the layer 3 processing, and now opening up capacity for traffic that really does require the layer 3 processing. So that's one of the key drivers to OTN in this new network. Also, what we find is the facilities that the customers, each of our customers has in our vendor community, are constrained by the physical HVAC, the power that comes into a building. One of my past jobs, I did facility planning, and you could be in downtown New York, and Con Edison will tell you you're capped. They can't bring any more power into that facility. So what do? You end up having to move, which is even more costly. So one of the things that a lot of us in the vendor community have begun to look at, again, around the high consuming power equipment, is there a way, what is it, and is there a way to better utilize that equipment for what it was designed for? And in the case that I just talked about with the routers, if truly 40 to 60% of traffic in a given router is bypassed, if you can remove that, then it takes the power consumption down substantially and gives you a longer time on a growth curve to be able to support layer 3 based traffic. This is just a comparison of the varying different technologies and their power consumption, and a breakdown. I know it's an eye chart. I'm sure you guys will have this available to you so you can see the breakdown of the varying different areas. But as you move down the technology hierarchy, power consumption goes down as well, and you get more efficiency. So again, the key here in designing and developing networks and equipment to go into networks is trying to figure out architectures that balance these technologies. You may not use all of these technologies, but you may pick 2 or 3 of these technologies and play that balancing act to get the most functionality out of a given network, but also the most cost efficiency to be able to repair, as I described in that previous slide, the traffic growth cost curve versus your revenue curve. So, carrier applications that are coming up, we're seeing more and more optical wavelength type services. Financial institutions are taking advantage of these from our customers. Video is also going to take advantage of that optical wavelength service, being able to transport video across a network. You may find that the likes of AT&T or Verizon may offer optical wavelength services, and smaller operators would be able to then utilize those services to pass their video across that. Also, the key in any business is to differentiate yourself from someone else. And with OTN, you've got enough intelligence to be able to offer SLAs, being able to go to your customers and guarantee certain performance, and being able to get information from the network to be able to prove to the customer that you are in adherence to your SLAs. Also, OTN brings in the ability to integrate in multi-domain networks. So, varying operators can now go and interoperate with each other across a common standard architecture and be able to, get traffic from one place to another. Particularly some of the smaller operators can now, in their consortiums, be able to utilize this to be able to pass traffic across the country without having then to acquire services from a larger carrier, thus, also keeping control on their costs. I think one of the things that you find in a lot of conferences, you hear this probably in the last 2 years, is being able to build up ecosystems and sustainable ecosystems where you have various vendors, operators, customers being able to exist at all levels and have a method of being able to provide, services up and down the chain in a way that brings back into control overall costs, no matter at what layer of that eco chain you're talking about, in order for us to be able to, as an industry, be able to support the continuous growth that we've been seeing and the dynamic growth that we have seen over the last several years. That's all I had for this afternoon. I welcome any questions that you have on this topic or anything in the core transport arena.
Is the updated presentation on the website?
I will check. We'll make sure. I had submitted this presentation, and apparently there was a mix-up, so we'll make sure that this is up on the website.
I saw the slides that you had were more recent, so thank you.
Any other questions? All right. Well, since I'm standing between you and probably dinner, I can give you all half an hour back in your day. Appreciate your attending this session, and have a good rest of the conference.